else. But yeah, it is a morning session in Korea. And so in the morning session, we are going to have two speakers. One is Professor Dawei Lu from SUSTech, and the other with Professor Kap-Kyun Jung from Seoul National University. And the first speaker will be Dr. Dawei Lu from SUSTech, and he will be discussing about experimental quantum principal component analysis via parameterized quantum circuits. So I wish everyone welcome his presentation.
Good morning, everyone. First, I would like to thank the organizers for this wonderful symposium on quantum machine learning and giving me this opportunity to present our recent work. And additionally, actually, I'm quite surprised that our host, Professor K, can pronounce our university in the right way, SUSTech. It's a relatively new university. In fact, after 5 days, this university will have its 10-year anniversary. Today, I'm gonna share our recent experiment in quantum principal component analysis via parameterized quantum circuits. Unfortunately, this work is not on arXiv yet due to some reasons. But it's and the second round review in physical review letters. I hope we can get a good news, and then you can see it online as soon as possible. And here is the outline of this talk. First, I would like to briefly introduce what is a principal component analysis. We call it PCA now. And second, what is the quantum version of PCA using the parameterized quantum circuits? We can call it PQC. That's a QPCA via PQC. And the last part is our experiment in this QPCA for the task of face recognition. We all know that when machine learning meets quantum science, there's a big explode. Now, people, I guess a lot of people get not so excited when they hear a lot of so-called exciting news in classical machine learning, like in the Go game, the AlphaGo beat the world champion Lee Sedol, the Korean, chess player, several years ago. And now people hear a lot about news about self-driving car, but a lot of people, when they hear the machine learning breakthroughs, they just keep calm. They think it's Euro. But if you connect the quantum information science with the machine learning techniques, people may get excited. Wow, it's a new route. It's the future. Then what is quantum machine learning? This figure is from Wiki, and it summarizes that you can have a classical quantum type of algorithm and classical quantum type of data. So here, for quantum machine learning, we usually refer to first the red one, the quantum data and classical algorithm, which means the problem is quantum and the tools you use is classical. And a famous work is by Matthias Troyer to solve the quantum many-body problem with artificial neural networks. And another aspect of quantum machine learning is the reverse one, where the problem is classical, but the tools you use is quantum. And I think the most famous one for this CQ application is a quantum algorithm for the solution to linear systems of equations by Seth Lloyd and his colleagues. Although it's not directly related to quantum machine learning, but it's so widely used in many machine learning tasks. And now people say for the first one, for the red QC one, people have an example to show to describe this. It's like you can think with the rapid growth of the GPU power, machine learning becomes a very useful technique in recent IT technologies. It's like a new hammer, and your quantum tasks are like nails. Now people are trying to find where are nails that you can use this new machine learning hammer to knock. So I really like the this way of description. But in this talk, I'm gonna focus on the yellow one, that is CQ, where the problem is classical and the method is quantum. In 2017, there is a very good review paper on quantum machine learning by Jacob Beaumont and Seth Lloyd and the colleagues. In this paper, they summarized the quantum machine learning, the machine learning algorithms that have the quantum speed up in a table. You can see that there are not so many algorithms that promise quantum potential. And in experiment, there are fewer. One worth mentioning one is a realization of a quantum support vector machine using the NMR system, where the people use an NMR processor to a 4-qubit one, and to recognize the handwriting 6 or 9. You can see here when the NMR peak is up, that means it's a handwriting 6. When it's down, that means it's 9. And in this talk, I'm going to focus on the QPCA algorithm and experiment. And with respect to PCA, it's invented by Pearson in 1901. And its category is, it belongs to unsupervised learning. The purpose of PCA is to reduce the dimension of the original data. And the procedure is to use the orthogonal linear transformation. It has many applications in quantum machine learning. And for example, if you have a 3-dimensional original data, and in PCA, what you do is you try to find 2 axes which are orthogonal to each other. We call them PC1 and PC2. You find 2 axes and project your 3-dimensional data onto this 2-dimensional subspace spanned by PC1 and PC2. And the requirement is the 2 axes must be orthogonal to each other, and the variance of the data after projecting them onto the 2-dimensional space should be as large as possible. It means you can recover your array from lower dimensional one as much as possible. And this is an example that you use PCA to map to realize the dimensionality reduction. And the procedure is, it's a little bit mathematical, but I will try to introduce it as brief as possible. So suppose that you have a data set, this is the original one, m samples. And for each sample, there are n dimensions. So in total, the data set is n by m matrix. Then what you do is you calculate the so-called variance matrix, n by n. That's easy. Like you just, use n by m original data minus its average, to center the average point to 0. You use the original data to multiply its transpose. N by m matrix, m by n matrix is n by n. So this is called covariance matrix. And the diagonal elements of the covariance matrix means the variance of the dimensions of the same dimension. That's the meaning of the diagonal elements of this same matrix. And the off-diagonal elements of this same matrix means the relation between 2 dimensions. What you do next is you do eigen decomposition on this covariance matrix, and you list the corresponding eigenvalues in descending order. And you list its eigenvectors as V1, V2 to Vn, and their corresponding eigenvalues are lambda 1, which is bigger than lambda 2, bigger than lambda n. And then you just pick out the first k eigenvectors and the first eigenvalues because they are big, they are principal component. Then you just pick this k eigenvectors out, which means you will form a new matrix. You can call it projection matrix. It's only k by n. From the covariance matrix, n by n, now you reduce the dimension to k by n because you only pick out the k eigenvectors that has big eigenvalues. And if you apply this projection matrix P onto the original data set, you can say it's k by n, and the original data set is n by m, and the multiplication will give you k by m matrix. Then you finished the reduction of dimensionality. Before sample, you have n dimensions. Now for each sample, there are still m samples. You only have k dimensions, which is much lower. So that's a basic procedure of PCA. And if you are sensitive enough, you can figure out where we can realize the quantum speedups. That is step 2 and step 3. Because in step 2, you can find that this definition of C matrix means this matrix is semi-definite positive because it's some matrix times its transpose. Since it's semi-definite positive, it can be represented by some quantum state, rho. This state is usually a mixed state. And next step is you do the eigendecomposition. And in eigendecomposition, there was a quantum algorithm to realize the speedup. So here, you can use a quantum process to replace the classical one for the potential speedup. I can give you a simple PCA, classical PCA example in user portrait analysis. Suppose that we have 4 people, Jack, Tom, Mary, and Lucy, and they have some dimensions, 1, 2, 3, 4, 5, 5 dimensions here. And this is a training data set. And you know that Jack and Tom are not your target users. Mary and Lucy are your target users. And the problem is, if I give you the 5th person, Jerry, and give you his 5 dimensions, can you tell me if Jerry is the target user or not? And here, first, we do not data normalization. We normalize the 5 dimensions for each sample with the average value 0, and they all locate in the -1 to +1 region. So we make equal weights for every dimension. And then we calculate the covariance matrix. There are 5 dimensions.
So I think the internet connection is a problem. So we're gonna wait just for a sec, for a minute. Okay, so probably he's coming back.
Only 2 dimensions. Then you plot these values on a 2-dimensional plane, and you find that the distance that the smallest distance is between Jerry and Jack. And because Jack or Tom are not target users, so Jerry is not a target user either. So that's a basic procedure of the classical PCA. And the part 2, a quantum PCA. So now we know that there are a few problems if you want to transfer the classical PCA algorithm into its quantum version. The first one is, we know that C is semi-definite positive, but how to map this covariance matrix into a quantum state? How to load the classical data into quantum registers? Basically, this is very, very hard, as it's not solved yet. In 2008, some people proposed the quantum RAM algorithm. This is, in fact, a bucket brick architecture, but if you want to put it into practice, there are several serious caveats in this method, and the caveats are summarized in the review paper. And the second problem is we know we have to do eigendecomposition on the same matrix. Then how to do the eigendecomposition? More than 20 years ago, Abrams and Lloyd, they proposed that a quantum algorithm may provide exponential speed up to increase the speed for finding eigenvalues and eigenvectors. But if you notice the red line here, in this paper, they say that they can only find eigenvalues and eigenvectors of a local Hamiltonian. Hamiltonian means dynamics, but same matrix means a quantum state rho. They are different. Although the state and Hamiltonian are both Hermitian, but Hamiltonian means you can control the dynamics. For quantum state, you can only have it as the input data. That's totally different. So we can have that is, if you can put the input state rho onto dynamics. In other words, I realize e to the minus I rho t, where rho now behaves like a Hamiltonian. Then you can use the previous algorithm in the last slide, and you can do eigendecomposition with a quantum speed up. And in 2014, Lloyd and his colleagues, they published a paper on quantum principal component analysis. I mentioned Lloyd so many times, so I decided to put his figure here. Looks like a cowboy. In this paper, the core equation is this. That is, the right part is like the dynamics of a Hamiltonian, where rho plays as a Hamiltonian. And the left part means you only have rho tensor sigma as a state, but you just apply e to the minus is dot t, where s is a swap operator. That means if you can have the time dynamics of a swap operator, then it's equivalent to realization of the e to the minus I rho t. If you repeatedly apply the equation, the last equation, with n copies of rho, then you can construct this dynamics, which means you have rho on the dynamical part as a Hamiltonian. Then you can use the quantum algorithm to find the eigenvalues and eigenvectors. But in this algorithm, we require multiple copies of rho, and we also need quantum-based estimation. So it's very difficult to realize in experiment. We try to use this Lloyd's algorithm, but it's too hard for recent experiment. So what we do in our experiment is, let's go back to problem 2, the eigendecomposition in this QPCA. That is how to do eigendecomposition of a state rho. So we use the parameterized quantum circuit. If you compose rho in its eigenbasis, and we list the eigenvalues in the descending order, the problem is, if you can find some unitary, we call it UG. If we can find some UG to transform this rho to basis, to the computational basis, then you only need to measure the values in the computational basis. And if we measure its value, then we get the eigenvalues of this rho's eigenvectors. So the problem now is, you really find UG to map the rho onto its computational basis? The answer is yes. If you can define an observable, and this observable, let's call it P, it's also Commission. It's a semi-definite positive. And it has totally different eigenvalues. For example, the simplest observable is like this. It's a diagonal matrix elements where each element is 0, 1, 2, goes to n minus 1. So this is a big n-dimensional matrix. its form in poly basis is quite simple. You can see you just have a sigma z poly element in every term and with weights. And we can prove that if you find some way to minimize the objective function of this one, then you can diagonalize the original covariance matrix rho into its computational basis. You see that we have the original state rho, and we try this u rho u dagger times p, where p is defined here. If you can minimize this objective function, then rho is diagonalized by this u. And this is proven by the Bock-von Neumann theorem and the rearrangement inequality. I leave the details into my paper. So the problem now is to minimize this objective function. And you can know that. So if you want to minimize objective function, you can use the parameterized quantum circuit, because the unitary evolution you see that can be performed by a PQC, like this one, depending on its expressibility. So like this one has a big expressibility. You can see that there are only parameters as angles in each block. Only the angles can change. If you want to optimize this PQC, what you do is you apply the PQC with some random initial guess, and you measure the objective function L. If it's not good enough, you again measure its gradient. You measure the objective function, its gradient. If it's not good enough, you go back to update your angles theta on a classical computer. If it's good enough, that means you finish the optimization. So it's actually a hybrid quantum classical control where the PQC is a quantum processor, but the updating of parameters is finished on a classical computer. And here is code, the pseudocode for this optimization, where every time for every measure objective function, if it's not good enough, you change your parameter theta with along its gradient direction, and you measure again. And unless L converges to a minimal value, then you just keep on doing this iteration. And the last part is our experiment. So for face recognition process, it's slightly different compared to previous user portrait analysis, because to recognize a people, for example, it's the training data. This is an image in the training data, so it can be represented by a 100 by 100 grid scale. You can reshape it in a 10,000 times 1 vector. Then if you have, for example, 4 images in your training data set, so the matrix is 10,000 by 4. So it's a covariance matrix is 10,000 by 10,000. That's too big. If you want to do the eigen decomposition on a recent quantum experiment, that's too hard. It's 10,000 by 10,000. But what can you do? Like this way. This method was proposed by Turk and Pentland in a classical computer science paper in 1991. What they do is they reverse the order of the multiplication. Before it's A transpose, but now they calculate A transpose A. You know, for this original data, if you calculate by A transpose A, you can only have a matrix with dimensions 4 by 4, which is very small. But why do you do this? Because this D, A transpose A, if its eigenvector is, say, psi I, and eigenvalue is lambda I, if you put the A before the left hand of this equation and the right hand of this equation, and you know that AAT is say, that is what you want. So that means say A psi I equals lambda I A psi I, which A psi I is in fact the eigenvector for C matrix. So if you can have I, which is only 4 by 1 eigenvector of D, and you just multiply A, the original data on this eigenmatrix, you will have the eigenvector for the C matrix. And you know that if you have 4 samples, have 4 eigenvectors, 4 psi I here. So you only have 4 eigenvectors of this C matrix. That's the principal component analysis. You know, this C matrix, so basically it have 10,000 eigenvectors, but now you only keep its first 4, which means you have 4 faces. We call this matrix as eigenface matrix. And in experiment, we use 4 spins in the NMR setup, where the nucleus spin, the spin-half nucleus spin, can be used as qubit. And we use this 4-qubit quantum processor with 1 carbon-13 and 3 fluorine-19. And this is our spectrometer. And the basic experiment is straightforward. It is someone sit behind a computer, and then it generates the radio frequency pulses to excite your sample, and you just load the RF pulses onto the pregnate, and it has resonance with the sample. And the dynamics of the sample is recorded by the pulses, and the pulses go back, so you can receive and process the signals. That's the basic procedure of an NMR experiment. It's quite mature. And in experiment, we have training images. You can see we have 2 people with 2 emotions. And we first calculate the eigenphase matrix, which is only 4 by 4. And we load this 4 by 4 matrix onto our 4-qubit quantum processor, and we use a 2-layer parameterized quantum circuit plus the hybrid quantum classical iteration algorithm, and to process the data. And finally, we minimize the objective function. Then we get the eigenvalues and the vectors of this D. It's only there are only 4 eigenvalues and 4 eigenvectors. Then we multiply the original data on the 1 eigenvector, so we get 1 eigenvector of the covariance matrix C. Now the dimension is 10,000 by 1, so this is 1 eigenvector of C. We only have 4 eigenvectors because we only have 4 psi j here. Because psi j is an eigenvector of the D matrix, so we only have 4 eigenvectors. So that's finished the principal component analysis. Then this 4 eigenvectors of C means 4 faces, right? So let me skip the details. 4 eigenvectors of C also means 4 faces. We call them eigenfaces. So actually, for each eigenface, it's a combination of the 4 faces in dataset. So you can deeply look into the faces. You will say for each eigenface, it has characteristics of each training phase here. And we also choose a test data set which also contains 4 phases. And for each phase, we just compute its weight vector, where is the eigenphase matrix times this matrix. And this one only gives you a 4 by 1 dimensional vector, which is quite small. For each training phase and for each test phase, we calculate their weight vectors respectively. Then we compare the distance between their weight vectors. You can test phase, its distance to the training phases are listed here. And this one is the smallest one, which means this test phase is closest to this guy. Then we finish the phase recognition. And for this one, it's close to this guy. For these 2, they are closest to this guy. Then it's done. And we also simulate our parameterized quantum circuit with different models and more layers.
Hi, Dr. Lu.
Basically, here,
Dr.
if
Lu?
you have more layers, like 5 layers, you will have
Yeah, Dr. Lu?
better optimization results. But it also requires, more experimental complexity.
Dr.
Okay,
Lu?
here is a summary. We propose a new quantum PCA approach using the parameterized quantum circuit. And the advantage is that we don't need the multiple copies of the quantum states or quantum phase estimation, which are hard to realize in experiment. And the second, we do a proof of principle experiment for phase recognition. We have 4 phases in the training data set, and we also have 4 phases in the test data set. And there is also an open problem here. That is, in this experiment, we can see that we don't have any quantum speedup because we don't know how to encode the classical data onto the quantum state. So we don't know how to realize quantum RAM. Because this experiment only involves 4 qubits, then it's easy. But for a bigger system, we don't know how to do this yet. But it's not the problem that we focus in this work. Okay, and for this work, I would like to acknowledge my colleague. This guy did the experiment, and this proposed, Dr. Dong proposed the quantum PCA algorithm, and Dr. Cher is a student from computer science. He provides us the example of the face recognition, and I also like to thank my funding agencies. Okay, that's all. Thank you.
Well, thank you very much for a nice and interesting presentation on PCA. Do you have any questions from the audience? In the meantime,
so can I ask questions? So Dawei,
please go ahead.
Thank you very much. I think it's actually very the work is very interesting. I actually have many questions, but running out of time, so maybe